Hello and welcome to the Chemistry Academy. In this video we're going to go over fuels in relation to the National 5 chemistry course. So just to get started, there's a few definitions that we need to know for this subtopic. So it's a good idea to get these on some flashcards, write the word on one side and the definition on the other, and then you can play a little revision game with yourself by having either side visible. So you have the definition and you have to guess, not guess, but know the term, and then you can also have you display the side where you have the term visible and then you have to recite the definition. You can also get friends, family to do it with you, like a wee quiz. So the main definitions you need to know are the definition of a fuel. So that is a substance that burns in oxygen to release energy. So these are things you really need to know word per word. Changing words slightly can sometimes mean that you don't end up getting the marks. So quite often with the fuel definition, people will say a fuel is a substance that can produce or create energy. That's not the case. You can't create energy. Energy just exists and it just changes from one form to another. That's going to take us into the realm of physics, so we'll just go as far as that. So just try to remember, a fuel is a substance that burns in oxygen to release energy. Okay. Then we've got hydrocarbon. So a hydrocarbon is just a substance that contains only hydrogen and carbon atoms. So that's why it's called a hydrocarbon, kind of just done a word. We've taken hydrogen and carbon and put them together. So that's what hydrocarbon is. An exothermic reaction is a reaction that will release heat energy, so it will feel hot if you touch it. And an endothermic reaction is the opposite. That's a reaction that takes in or absorbs heat energy from the surroundings, and therefore it will feel cold when you touch it. So examples of these reactions in everyday life: if you've got hand warmers, they create an exothermic reaction within the sachet. So when you burst the wee thing in the middle or crack it up, that starts the reaction, and then the heat energy gets released to the surroundings, which then makes it feel warm for you to touch. An endothermic reaction example would be the opposite of that, where we get the ice packs that you crack to get them to go cold. So again, when you crack them or burst the wee packet inside of them, the endothermic reaction will start, and therefore it absorbs heat energy from the surroundings, so it makes it feel cold. Okay, exothermic gets asked about more than endothermic, but just make sure you do know both of them. So that's the main definitions really. So like I said, get them on some flashcards and get learning them. So if we then go on to how the fuels burn to release energy. So when a fuel burns, it does so in a combustion reaction. So the reaction of anything burning in oxygen, which I've got here, is classed as a combustion reaction. So if you see a substance reacting with oxygen, it's quite likely that it's a combustion reaction. It isn't always a combustion reaction because there are other things that involve reacting with oxygen, but it is a potential that it is a combustion reaction. In order to identify if a reaction is actually a combustion reaction or not, we then would go and double check what the products were. Okay, so we're looking for oxygen as a reactant, but then there's also certain products that we'd be looking for. So in the case of what we call complete combustion, so this is the combustion that you normally would come across. The complete combustion happens when you have a plentiful supply of oxygen, so there's lots of oxygen around. It's really easy for stuff to burn because everything is burning in the oxygen. So the more oxygen you have, the more likely the combustion reaction will be complete. Complete combustion is when the substance burns in oxygen and the products are carbon dioxide and water. Okay, so that's the key products of complete combustion. However, this is only if you burn like a hydrocarbon, so something with carbon and hydrogen, or like say an alcohol that's got carbon, hydrogen and oxygen in it. Those are the products you tend to look for when you're looking to see if a reaction's a combustion one. You want to see carbon dioxide and water and oxygen as the reactant. So carbon dioxide, water is the product, oxygen is the reactant. And that's for if it's complete combustion, where you've got a lot of oxygen present. Like I said, if you have some other elements present, you can sometimes produce other things. So we're going to go through some examples here of combustion reactions, so where things are reacting with oxygen and work out what the missing products would be, just so you can see how it kind of works. So if we look at this first example, we've got two carbons, or C2H6, so that's ethane, and it's reacting with oxygen. The 3.5 moles here doesn't really matter just now, I meant to rub it out. So basically what happens is every atom in the fuel, the thing you're burning, reacts with oxygen to produce something. So the carbon will react with the oxygen and makes carbon dioxide. That's the common carbon and oxygen compound that we know of. And then the hydrogen also reacts with the oxygen and produces water, which is another common compound containing hydrogen and oxygen that we know. So that's the products when you burn a hydrocarbon, something that just contains carbon and hydrogen. You make carbon dioxide and water. Okay, we'll not bother balancing this because we can come back and do that at the end. If we then look at this next example here, we've got a fuel with carbon, hydrogen and sulfur in it. Again, burning in oxygen. So we take the carbon, react it with the oxygen, and that will produce CO2 if it's complete combustion. The hydrogen with the oxygen would make the water. And then this time we've got sulfur to react with the oxygen. So that makes a gas called sulfur dioxide. Now, sulfur dioxide gas is very bad for acid rain, so it's harmful for the environment because it causes acid rain. So what happens is the sulfur dioxide dissolves in rainwater and produces sulfurous acid, and therefore when the rain comes down it's acidic and it can kill a lot of plant life and damage aquatic systems and things. So that's the gas you need to remember as the one that causes acid rain. Okay, so really you shouldn't be burning fuels that contain sulfur, because if we burn any fuels that contain sulfur, we end up producing sulfur dioxide, which is harmful and causes acid rain. Okay, so usually we would not use as a fuel, and you would remove the sulfur first if you could, because of this problem here. Okay, if we then look at this example here, so I've kind of done this back to front, that should technically really be a gas because it's a hot environment. So this time we've produced water. Water is the only thing we've produced. That means we can work out what the fuel must have contained. So we know the oxygen comes from the air, so that's not necessarily going to have been in the fuel. So the only element that's left is hydrogen. The hydrogen are the only atoms left that we need to have in our reactants. So the fuel must be hydrogen gas, which would be H2 because it's diatomic. So any element in the products that's not oxygen must have been in your fuel. Okay, because atoms can't be created or destroyed, they have to just turn again from one compound to another. So if you had hydrogen atoms or carbon atoms in your products, you must have had them somewhere in your reactants. But the oxygen can come from the air, so it's not necessarily always in the fuel. Okay, so just put a wee note here, any element other than oxygen in the products must be in the fuel, okay, or the substance that's burned. Then we've got this experiment here that you'll see sometimes. Just come to this side. So this is where we've got we're burning a fuel or substance and we're trying to identify what the products formed are to help us identify what the fuel might be. So the first collection bit is usually where you've got an ice bath, so cold water around that container. So when the gases that are being produced when the fuel burns, they'll travel through the tubes here, and then when they get to this cold beaker, because it's surrounded with an ice bath, sometimes you will get a colourless liquid forming, okay? And that's because gases have condensed and formed a liquid. if you get a colourless liquid, that means you have produced water. Okay. So if you get a colourless liquid in that container, then it means you produce water when you burn your fuel. Then the rest of the gases that haven't condensed will keep going along this tube until they get into this test tube of lime water at the end. Hopefully you remember that carbon dioxide turns lime water cloudy. So if the lime water goes cloudy, it means you've made carbon dioxide. If it doesn't, it means you've not made carbon dioxide. Okay, so what does this mean? Well, if we've produced water and carbon dioxide, so you get a colourless liquid in here and your lime water turns cloudy, you must have had a hydrocarbon at least that you burned, okay? Because you needed to have carbon and hydrogen coming from somewhere to produce the water and the carbon dioxide. If you find that you produce a colourless liquid, but the lime water does not turn cloudy, it means you've made water, but you haven't made carbon dioxide. So that means whatever you've burned must have contained hydrogen, the hydrogen that's in the water, but you haven't had any carbon in your fuel. So it's most likely that you've burned hydrogen fuel, or maybe something that contains hydrogen and other atoms but no carbon. Okay, so that's how identifying what the products of combustion are can help you work out what elements must have been in the fuel. Because like I said, any element other than the oxygen must have been in the fuel that you burned. And if the element's not in the products, then it can't have been in the fuel either. Okay? That's not to say that the fuel can't contain oxygen. Of course, we know alcohols are very good fuels and they contain oxygen. But we just can't say for sure when we're burning a fuel and identifying the products that there is definitely oxygen in the fuel, because the oxygen could be coming from the air. Okay, so that's generally complete combustion. Like I said, we could have balanced these equations, but we'll save that for the balancing equations video. So what we're going to do now is talk about another type of combustion reaction that's not complete combustion, but it's known as incomplete combustion. So this is where we have a limited supply of oxygen as opposed to a plentiful one. So for incomplete combustion, this is, like I said, when you've got a limited supply of oxygen. And this is where the substance will still burn in the oxygen, but because you've only got a limited supply of the oxygen, you'll only produce carbon monoxide, so CO rather than CO2. A carbon soot, so that's like solid black carbon, everyone usually knows what a soot is. And then also you will make the water as well. So if we take the ethane that we had before and burn it in a limited supply of oxygen this time, then we will make the carbon monoxide, carbon soot and water. The problem with this is that carbon monoxide is extremely toxic to humans. It will actually kill you because, you don't need to know this for chemistry, but just for general interest, the reason it kills you is because it attaches to your red blood cells, because it has a similar shape to oxygen. So your red blood cells start carrying the carbon monoxide around your body instead of oxygen, and essentially you kind of suffocate because your muscles and your body's not getting enough oxygen. So most houses now will have carbon monoxide detectors in them, because it's known as the silent killer, the silent assassin, because you could be sitting in your house if your boiler's broken and it's not getting a plentiful supply of oxygen in it, the fuel in your boiler's not burning properly, you could be producing carbon monoxide and it's going into your house, and then eventually it could potentially kill you. So there's a lot of carbon monoxide detectors in houses these days as a legal requirement for this. So just remember that gas, carbon monoxide, is toxic, poisonous to humans. Carbon soot's just not good for the environment either. It's also, if you were in your house, it's not good for your lungs because it's black solid soot you could be breathing in. So we want to avoid incomplete combustion whenever we can. Okay, so the main things you need to know about that is being able to identify if a combustion reaction is incomplete. and that would be looking for carbon monoxide as one of the products, as well as potentially soot, and just knowing that that's what we produced if you were burning something in a limited supply, and also knowing that the carbon monoxide is classed as being toxic. So just to finish off, we're going to go through a few different types of fuels that you'll come across, just give you some of the pros and cons to them, because this can sometimes be asked about as well. So we start off with the fossil fuels, and mostly these are cons. So we've got coal, oil and gas. Coal comes from the land, we mine for it on land. Oil and gas come from out in the sea, so that's where all the oil rigs go out and get the oil and the gas. Of course, everyone knows that fossil fuels are harmful to the environment, but you need to be a bit more specific than that if you're asked about it in your exam. You need to specifically relate it to that they produce a lot of carbon dioxide, which would contribute to global warming. Or you can say that they produce a large number of greenhouse gases like carbon dioxide. Okay, so you need to be as specific as that if you're asked about why a fuel is good or why it isn't. You need to link it back to what's it producing and is that good or bad for the environment. The other problem with them is that they're known as being finite, so that word means that they will eventually run out. I just realised I didn't close my bracket here. So that's another not great thing about them. We're going to eventually run out of them. However, the good thing about them is they do have a lot of stored energy, so they are very good fuels. Like, they give us out a lot of energy, so despite them not being good for the environment, they have a lot of energy in them, which is what you're wanting a fuel to do, is to release energy. So that's why we've used them for so long, really. But really, fossil fuels are not good. Then we move on to alcohols. So alcohols are any alcohol you can use as a fuel. The good thing about all of the alcohols is that they have less chance of complete combustion taking place because the molecules themselves contain oxygen. So this is methanol here. As you can see, it's got an oxygen atom in it. That means that you need to have less oxygen coming from the air in order to produce your carbon dioxide, CO2, and your water. So people say they burn more cleanly. What that really means is that they're less likely to undergo incomplete combustion, so there's less chance of soot and carbon monoxide being produced. And it is because, like I said, the molecules themselves have oxygen atoms in them, so you need less oxygen atoms coming from the air. The other one that's a positive, but this only really applies to ethanol, is that ethanol is renewable. Because we make ethanol from plant material, and then if we burn the plant material, it turns into carbon dioxide and water, and then plants take back in the carbon dioxide from the atmosphere eventually, it creates a renewable cycle. So the ethanol is renewable. All the other alcohols technically aren't renewable though. The bad thing about them though is that they do require you then growing crops, and that can take up land mass that could be used to grow food otherwise. Because if you're growing the crops just to produce fuel, you're not, for like cars and things, you're not growing it to produce food for humans. So that's one of the downsides of it, is the big land mass it does take up. And then lastly, we've got hydrogen. So it's a renewable fuel because it burns to produce water. And then we've got obviously the water cycle, and we can take the water and split it back up into oxygen and hydrogen to make the hydrogen fuel again. So the good thing about it, as well as being renewable, is that it's not harmful to the environment because, like I said, it only produces water when you burn it. So there's no greenhouse gases there's nothing that's harmful to the environment, nothing that's toxic to humans. The downsides to it though are that it's quite expensive to make the hydrogen in the first place. And also there's just quite a high risk of explosion that comes with it. I don't know if you ever did the hydrogen balloon when you were in like first year of science, and I'll try and find a video of it and put it here. Basically, if you have a balloon of hydrogen and stick a flame near it, it just goes poof, like massive explosion. So if you were to crash your car, that could be potentially what would happen if there was any ignition source near your fuel tank. So lots of work went into that for making it safer as a potential fuel. So that'll just be to do with how they design the cars and things, how they would get around that. So yeah, the last thing we're quickly going to touch on is fractional distillation, though doesn't always come up, but it might, so I'm just going to quickly run through it just so that you are aware of it. Finishing up with fractional distillation, so when we take oil out of the sea, it comes out as a big mixture known as crude oil, and it basically contains lots of different lengths of hydrocarbon chains within it. Now the crude oil is actually no use when all of those hydrocarbons are mixed in together. It's only useful when we separate out the different sized hydrocarbons into different sections and use them separately. So this is what we would call a fraction. So a fraction is a group of hydrocarbons of similar length that can be used for a certain purpose. Now, fractional distillation is just a form of distillation where you increase the temperature and allow things to separate based on their boiling point. That's how distillation works. We essentially heat up a mixture until certain things start to boil off, because every different substance has a different boiling point. So on an industrial scale, fractional distillation, you have the big massive fractional distillation tank, and it's cooler at the top than it is at the bottom. At the bottom it's very hot, at the top it's much cooler. And you'll notice that all the way along there's different levels that have sort of different bits that have you can collect things off. And each of the different levels, with their own different tap if you like, is known as a fraction. So at the very top you get the molecules that have the lowest boiling points, so they evaporate the easiest, turn into a gas, and that's where you get the gases. So for example, like butane gas that you use when you go camping, things like that. So they all get collected off the top of the fractional distillation column. Then down the bottom you have really thick, gloopy substance, because the hydrocarbons are really, really long, and that is not actually used for tarring roads. So it's a really thick, gloopy substance. We can't use it as a fuel, we can use it to tar roads, and that's known as the residue. We then have all the different fractions in the middle that are used for different things you can see here. One that you'll sometimes get asked about is kerosene, which is used as jet fuel. So just remember that kerosene is the fraction that's used for jet fuel. Other than that, you've got petrol and diesel, and you've heard about all these things in day-to-day life. The only difference between them really is the length of the hydrocarbon chains. Like I said, the smaller molecules have the lower boiling points, so they get collected at the top, and then the bigger molecules have the higher boiling points, so they would end up down at the bottom. You also will see here mentioning viscosity. Viscosity is just like how thick and gloopy something is. So the smaller molecules that are gas at the top have a very low viscosity, whereas the thick gloopy residue that's used to tar the roads is very viscous. Okay, so you really just need to remember that the smaller molecules have the lower boiling points and are less viscous, and the bigger molecules collected down the bottom have the higher boiling points and are more viscous. So I hope that helps you with fuels. If you found this video helpful, please give it a like. Don't forget to subscribe, and I'll see you again soon.